So, a very good day and warm welcome to all participants to this webinar event. My name is Kanendra, and I would like to welcome and thank everyone for joining us for this IEEE Power and Energy Malaysia Distinguished Lecturer Program. IEEE PES is a non-profit organization which gathers members who has power and energy related background. With the objective to create a platform for exchange of ideas and knowledge, IEEE Power and Energy Society Malaysia chapter has managed to sustain its activity, which would span from knowledge networking, industrial visits, distinguished lecture series, and technical conferences. Today, we have our distinguished lecturer, Professor Vikesh Pal from Imperial College London, to deliver his lecture titled Robust Volt-Var Control in Power Distribution. Our moderator for this event will be Associate Professor and Senior Dr. Ahmad Farid Abidin, IEEE PES Committee member. Right before we begin our event, here's a short clip on IEEE Power and Energy Society. Okay. With that, we would like to begin our event. I would like to pass this session to our moderator. Thank you.
Thank you, Dr. Kanendra, and good day for everyone who joined this distinguished lecture program. And I would like to welcome also for our distinguished speaker, Prof. Vikesh Pal. Okay, before we call Prof to deliver his lecture, I would like to read a little bit on our distinguished speaker's profile. Okay, Prof. Vikesh Pal is a professor of power system at Imperial College London. He is a research active in power system stability, control, and estimations. Currently, he is leading a 6 universities UK-China research consortium on resilience operation of sustainable energy system, ROSES, as part of EPSRC and SFC program on sustainable energy supply. He was the editor-in-chief of IEEE Transaction of Sustainable Energy from 2012 to 2017 and editor-in-chief of IET Generation from 2005 to 2015. Prof is a vice president, PES Publications from 2009 and until now. He is a fellow of IEEE for his contribution to power system stability and control. Prof. Vikesh is an Prof has published about 100 papers in books in power estimation and control. Two of his papers in power system stability and control topics have received annual Best Journal Paper awards. Prof. Vikesh was an Otto Monstedt Professor at Denmark Technical Universities on 2019 and Mercator German Research Foundation at University Duisburg Essen in 2005. He worked as a faculty at IIT Kanpur, India. He also held a visiting professorship at Tsinghua University, China. Prof, without further delay, give what we call it the event or the platform to you. You are going to give or deliver the topic on the robust Volt-Var control in power system. To you, Prof.
Thank you. Can you see my slide? Not yet.
Not yet.
Okay, share screen. Okay. Now?
Ongoing, Prof. Okay, now, yeah. Okay, Prof.
Yeah. So can you see it now? Again, that same issue. My slide is not moving, so can you see it
Or you
now?
want me to control the slides?
No, but can you see my slide?
Not yet, not yet.
Okay, so there is some issue then. I need to get back to this again to sharing mode. No, it looks, you cannot see my slide, right?
Not yet.
Don't know what to do. Let me see. Share screen again. Share screen. Window. Share. Are you able
Okay,
to
now
see?
the slides appear already. I can see the slides.
Okay, but if I go to the presentation mode,
Okay, now it's already.
can you see it?
Yeah.
And this is moving also.
Yeah, moving. Nice, very nice.
Okay. That is where is the problem. So I don't know what to do here. Stop sharing screen. Can you see it now?
Yep, I can see it.
Okay. So this is thank you Farid for introduction. This is on Volt-Var control in power distribution systems. The overview, first we'll talk about the statement of the BBC problem and then challenges. And then we talk about chance constant BBC framework. And in that Volt-Var control framework, we see that we need to have a convexification of the power flow model. And then that would be followed by scenario enforcement algorithms because we are to make it robust against uncertainties. Then we implement this BBC Volt-Var control in two-stage philosophy, and then we talk about the results and discussion for this scenario enforcement algorithms. Finally, we will conclude. So main objective of BBC problem is that we need to make sure that the node voltage should be between certain range. So that depends on the design standard, etc., and operating code of a particular utility. Typically, it can be 95% to 105% for the voltage, and as well as for the feeders of the cables, transmission or distribution feeder and cable, the capacity should not exceed. That is, current capacity should be less than the max. There could be some other associated objectives that is minimization of power loss, so that we could minimize the loss, and also there would be some tap changers operations because of the variation of the generations. So we could also minimize the tap counts for making sure that the life of the tap changer is not endangered. Control variables essentially switch shunt capacitor set points, tap changers and voltage regulator set points, and also we have the DG that will also have the reactive powers. So that is the the setup. It was like a voltage regulation responsibility of the DNO and line drop compensator. That was the traditional philosophy. Now, with more and more the distributed generations like photovoltaics and wind. At the end of the distribution, we now have more P and P coming in, and that will have issues about the voltage rise as well as fault contributions. Problem with that P is also it's uncertain. So naturally, we need to see how we could control this Q to make sure that the voltage profiles are maintained, and with many operating conditions, we are able to operate within the rated voltage range. Focus, we are going to take the forecast of the load as well as the PV error into consideration here, which has been ignored. So that means the problem will come from a deterministic solution Volt-Var control to stochastic Volt-Var control. That's how the chance constant framework is applied. We will also incorporate the output power of the DG as one of the say control options, and which is a fast control options. So deterministic VBC is this: minimize the power loss subject to power flow model. Node P and Q deterministic, they are nonlinear, and this is the range, and there is no forecast error. Chance constant, minimize the expectation of the power loss, because we are talking about many scenarios, so expectations. Power flow model, node P and Q, they are uncertain, and the probability that the node voltage is within this range must be greater than or equal to 1 minus epsilon, right? So our actually epsilon is a confidence parameter. So forecast error is considered. So this is the confidence. So probability that node voltage is within this range, and typically if you take epsilon to be 0.01, so it is 0.99, right? So 99% confidence, we could say that this is this. Challenge in chance constant, we minimize the Z power loss. The power flow model is non-convex, so no guarantee of a global optimum. And the probability of the node voltage, it is difficult to compute because this probability space is not well defined. Branch flow model, typically Ohm's law, node I, node J, voltage drop in the branch is the branch impedance into the current through the branch, and power flow is that V into Ij star. Nodal power balance is this, that Sj k is equal to J Sjk minus Sij Zij Ij square. So this is the nodal power balance, like here, whatever comes that goes, plus if you have any injections, etc., etc. So this one we could then say transform into square of this, so that gives you the square of the voltage, etc., etc. For power also you could have this, and for node power balance you could get the real and reactive component like this. So now we are getting some quantities like Vj square, Vi square, Ij square, and so on. So these variables or the quantities we could define through a new variable, so like Lij and Ui. So then that becomes the injection, power injection on the jth node. This is linear in Pij and Lij. For Q also, this is linear in Qij and Lij. For the voltage square, we have defined to be Uj. So this is also linear in volts Lij. But then Pij square plus Qij square is Lij Ui. So this is where there is a product of the two quantities that we have defined. So that itself is now, it's a product, so bilinear say constants. So linear, and then this one, this Pij Qij square Lij, what we could do, we could make from equality to, if we do inequality, so then what is the geometric say property of this Pij Qij square? It is essentially a second order cone, something less than that. So you then consider the whole of the cone. So then you could express that as Pij Qij Lij minus Ui Euclidean norm must be less than or equal to Lij plus Ui. So now this becomes sum of these two here. So that's the second order cone. We could then have a set of convex constraint here, and then you could apply the convex cone programming. But there is an issue with the that power injection, reactive power injection at node, that is square of the voltage, that is Uj, plus then there is also a BCJ, that is the susceptance of the capacitor bank. Now that BCJ is a discrete quantity, that is, it is not a continuous variable depending on the number of banks. So a discrete quantity with this Uj, so that actually is a product of continuous and discrete variable. So we need to have, say, some kind of treatment to handle that. So what we defined actually some new quantity Z 1 to n, that is number of, say, capacitor bank position, discrete set position. It could be also transformer set position. Then that is we define to be ZJK. So what will happen is at any point of time, there will be only one capacitor bank you will select. So that would be 1 and the rest would be 0. So then we define this a new quantity Wj, which is this into Uj. Now this that becomes, you know, BCJ Wj. So this essentially Wj BCJ BCJ Uj or Zj Uj is defined to be Wj. So then this becomes BCJ Wj. So how we handle this? So whenever there is a big M method, so whenever ZJK is 1, that is when you have chosen that particular bank. So this is Uj, this is the constraints we call big M bilinear terms, a big M method for bilinear terms. So this is a large value of M, it can be nearly infinity, but moment you put that Z is equal to 1, so that disappears. So Uj is less than Wj is less than Uj. This means Uj is equal to Wj. So that is this. ZJK here means Uj is equal to Wj. So this, you know, the that, and then this becomes redundant because we have already got Uj is equal to Wj. Now when we have, say, that particular bank not selected, so Zj is 0, right? Zj is 0. So 0 less than omega Wj less than 0. This means Wj is 0. So then again, you know, these constants are that way it's redundant. So Wj is 0. So that is not part of the say the constants. So now we need to see how we then handle the probability part of this. It is difficult to model this, but we could always have the forecast PV forecast errors from historical data, which is assumed to good accuracy. That's we could do. So then we need to generate lots of probability, lots of scenarios. So how we generate that? Depending on the binary variables and continuous variables and what confidence you need, that is epsilon, you could generate, say, number of scenarios, that n. This is how it will come, and this will be less than or equal to gamma. What is this gamma? So gamma is 1 minus gamma is the confidence, and 1 minus epsilon is the level of robustness. So one is associated with the scenario, level of robustness. Another is associated with the confidence that that our node voltage is going to stay within that bound. So these parameters typically can be 10 to the power minus 6. So this becomes 1 minus 10 to the power minus 6. So confidence can be very, very high, 99.9999%. And robustness is again like you choose a scenario, you have considered all the scenarios, I mean possible n number of scenarios, then you have designed your reactive power control scheme, and then there is always some scenario possible which you have not considered. So then what is the robustness of that solution? So how it can guarantee again effectiveness against those unconsidered scenarios. So this is the expected power loss sub, and also the tap new and tap old, the deviation of the tap into this, how you can get a multi-objective here. This, first of all, we have slow tap on-load tap changing controller and also voltage regulator and capacitor bank. So they're discrete controller, they're mechanical device, they're slow speed. So if we keep on changing them very frequently based on how the PV forecast, how the output from the PV is changing, so then what will happen is there will be lots of movement of the tap, which will lead to wear and tear. So then we could put a priority like W2 and minimize this part, that is tap new and tap old. This part has to be minimized, means new tap position should not be away from tap old like this. So this is called EPIGAP programming. So but this is the magnitude of that you're talking about. So naturally that can be captured by this minimize expression power loss W2 into T, but T is that tap new minus tap old. Tap new T must be less than or equal to tap new minus tap old must be less than or equal to T. That's minus T, less than this quantity without this magnitude, and less than T, and T should be 0. So that is how you transform this absolute function mode function to this one, and then you minimize this loss. So there are two things now. You could choose W1 to be 1 and W2 0. That means then you don't take care of the tap's life. But then also you could choose W2 to be say 0.5 and W1 0.5. So you are giving equal priority to both, minimizing power loss as well as minimizing tap deviation. So that we will see this. Now how we also capture the load here, because remember we have V square and I square. So if we have V square, means that's a constant impedance type of load, and constant power load is not function of voltage. So constant impedance and constant power load are very much part of this the convex equality. There you have this very well model. So it does not actually affect the convexity for constant impedance and constant power load. But moment you bring constant current load, so that becomes function of 1V. So that becomes again square root of Ui and Uj. So that means constant current type of load in that power injection equations cannot be represented maintaining the convexity, without disturbing the convexity structure. So we need to absorb that. So normally 50% of that constant current load can be absorbed as constant power, and 50% can be absorbed as constant impedance. That works. And there are many other ways to represent them, like list, say, so there is the binomial approximation. There is also least square estimates of this for that. And then we have done some work on that, and there are publications available on that too. How to transform a constant current load into an equivalent constant power and constant impedance. Now the scenarios, computationally, is too many scenarios. We got to then think about say selective number of scenarios. So if we can select say a handful number of scenarios which are able to represent more or less a huge scenario space, so that will be good that way. So how this then work is the perform base case VVC, find out the tap capacitor set point, and also the DG operating power relations. DG output power will have real power as well as reactive power. So there is a relation between the real power and reactive power, which is connected by this coefficient, which I will show to you. So find out these, and then once you get this Tij, Bcj, then you can form the Y bus matrix. Factorize that Y bus matrix to get I is equal to YV. So factorize that Y bus. So then get current, and then here are a lot of forecast errors that we already feed to generate these scenarios, and check whether the voltage node voltage criteria, node voltage say constant is violated or not. That is 0.95 to 1.05. Now, if there are violated scenarios, then what happens is we can see how many number of scenarios are violated. If there is no violated, if the number of violated scenario is null, that is this, then stop. You have done it. But if there is a violated scenario, that is, you design for a base case and then you are trying for many other scenarios, and some other scenarios are violating your voltage, nodal voltage limit. So then you collect all those scenarios, and from those number of scenarios, you could then choose a handful number of scenarios, add those scenarios into the solution space. That means each of the scenarios then also become part of the convex power injection, nodal power injection, constant equations. Then you run the scenario based chance constant VBC, find out a new AJ, BJ, and CJ, and then TIJ and BCJ, and then go back. And then go back to this here again. So you got a new set and get a new Y bars, and then again check against scenarios. Once you do this, then you will see that many of the scenarios that were violated while checking the voltage magnitude, now they are they are not doing so. So now number of violated scenarios would be less, and again go for scenario reduction and do this couple of times, and finally you will see that you are not violating any scenarios that you have done. So only the price that you pay is started with a base case TIJ, BCJ, AJ, BJ deterministic. Then you have come with a AJ, BJ, CJ, and TIJ, the control, which is now able to say address variation in the power injections. That is, you have added them into your constant equation, not like PJ. The jth nodal injection is now not one, it is also including another scenario like that. So many scenarios which are violated, they have been included here. That means they will be a bit suboptimal compared to this, but then the advantage is that they are able to guarantee that the constants are not violated. So this is what it is here. Perform BBC basic schedule, check violated scenarios, reduce the number of violated scenarios into some set. Like, I mean, what do you mean by scenario reduction? Like, say you have 1,000 scenarios which are violated. If you include 1,000, these scenarios, there will be 2,000 additional constant equality constant equations, so which will be difficult to solve. So rather than including 1,000 scenarios, you could have scenario reduction algorithms where maybe you could be able to represent this 1,000 scenario by about 10, and then use those 10 at the most dominant scenarios to the program, and then run scenario based chance constant. This is something like you have a three-dimensional say plane. What you need is this: you need to have three-dimensional basis vector 0, and so 1 0 0, 0 1 1, 0 1 0, and then 0 0 1. That x y z axis. So similarly, from all the set of reduction, you could come with couple of clusters, like have the say like projection statistics or Mohalanovic distance, or the distance between the center of couple of scenarios to another center. So like that you could always find. Now the two-stage control works like this. So every hour you know the forecast for the next 24 hours. So every hour in the beginning you do all your this optimization, and then you find capacitor and OLTC setting and keep it there. Don't change them every hour. So, and then next hour again you do and keep it there. So every hour maximum you need to have a change. But within the hour, what is happening? This is the reactive power of the DG, and that is varying with this, with the function of the PDG. Because we know that PV output is varying because of the irradiance from the sunshine or cloud cover, etc. So if that varies, so Q varies. Now, how is that? DG reactive power rule is QDG is A PDG square B PDG plus C. Now, you could easily see that if you make C to be 0 and then A to be 0, so QDG becomes B PDG. That is a constant power factor operation of a DG, isn't it? Q by P is B, So we know that tan inverse Q by P was actually that the power factor angle. So that's this. But we have a quadratic relationship here because you could do it because we have a convex optimization process here. So A PDG, B PDG, C. So this will give you that whole VVC gives you an optimal set of A, B, and C. And now at the beginning of the hour, you get your optimal set of A, B, C based on your forecast from P error. And then you see as this P is changing, so the Q also will change. So that way, the reactive power control from the DG is a fine adjustment, and then OLTC etc. They are kind of course adjustment at the beginning of the hour, whereas this is doing continuously. So we got two stages. One is happening always, and other one is happening once in an hour. So now you see that for a couple of cases, we got 95 bus test case, 123 bus test case, and 190 bus test case. So there you see that for deterministic case, you design your Tij and then say BCJ as well as AI, BI, and CI for the DG for a deterministic case, and then you check with all the other scenarios. Then you see then how it is moving, that yellow bars. So this is the VVP, voltage violation probability, is the fraction of the total node voltage violation across the MC trial. So now, like you have the number of Monte Carlo trials is NMC, number of node is for this 95. So that many number of nodes theoretically is maximum possible can be violated. But then you see how many is violated, NVVI. So how do you count NVVI? You just look at number of the node voltage which is not in that limit of 0.95 to 1.05. So count those number for each of the Monte Carlo scenario, and then do it for the all of the Monte Carlo scenario. So that is the total number of node voltage violations, and this denominator is the maximum possible number of node voltage that you have for NC, number of Monte Carlo series trial, and then you do this, and you could put a percentage figure to that. So that gives you this. So as you move along, and what is this? Along this, the happening is standard deviation of the forecast error. The forecast error, if it is like 10%, so then this is this. When it is 25% forecast error, then you see that so many cases it is violated. But this will happen because if the forecast error is not good, the forecast quality is not good, naturally you will have more and more violations. So now the green is when you have the chance constant. You see that virtually it is just maximum 3 or 4 it is violating. So that's the effectiveness of this chance constant Volt-Var optimization, where very less number of cases you have voltage violations compared to the deterministic cases. So that's the the contribution of this work. And now these two graphs are for another 123 node network and 190 bus network, and similarly for their green, etc., etc. So that's is the advantage of VVC. We also now go to the we mentioned that tap changer. We wanted to have a constraint on that. The number of changes. Say if you don't consider the tap changer as part of the objective, that is W2 to be 0, then you see that about 23 to 24 cases, number of times taps are operating there, right, in the whole say hour or something. Now then, if we have at 0.25, so this is about 17, and then if we have 0.75, this is about 5 to 7. So that means if we include the tap changer deviation as an unacceptable sort of situation with the inclusion of that epigraph programming and then putting that as part of the objective function, then we see that we are able to minimize the tap hunting also, or tap movement, which then indirectly uh, uh, improve the life expectancy of the tap changers. Typically, a tap changer should operate 30,000. After that, it has to be replaced 3,000, and then you have a normal sort of maintenance, annual maintenance, and then it goes like this. Okay, so that's the advantage of having both into this. Now, I said that all those scenario that we have considered as a constant has given us a suboptimal set of say Tij, Bcj, Ai, Bi, Ci, and that means that will have some impact on the overall loss. So what is that loss? Deterministic case is a loss is a PLDC, whereas the chance constant case gives fractionality in the network loss. So this is the loss in the network when you go for chance constant, and this is the loss when you go deterministic. So this is the difference between this, and then normalized with respect to the deterministic. So this is the expected value of power loss corresponding to the chance constant schedule. So there you see for different network model that we have considered. As you move along, this forecast error standard deviation more and more, then you see that percentage loss, the conservative index, this is increasing. So what is that actually? If you look at this percentage wise, this is moving between 2 to 8%. So the additional loss is 2 to 8% compared to the deterministic case. Generally, in a distribution systems, your loss, if the network is balanced, it would be about 5 to 6%, maximum 5 to 6%, maximum say 4 to 5%. Generally, TND loss is about 6%. So 2% transmission loss, so about 4%. On a 4%, then you are having this, 6 to 7% means 0.28% extra loss compared to the deterministic case. So if in a deterministic case, distribution loss is 4%, with the chance constant, this is going to be 3.72%. Deterministic is 3.72%. The chance constant will be 4%. So that's the conservativeness, because we have gone for suboptimal. But what we have done is we have been able to address the voltage, say within the limit of the grid operation code. So the remarks, the nodal uncertainty need to be considered in the VBC scheme. Chance constant VBC framework can be efficiently solved through scenario enforcement algorithms. So that could shows robustness performance. That robustness we talk about. That's epsilon, and then the confidence we talked about, that gamma. Voltage dependent load models needed for improved convex solver, but we have done that, I said to you in that. So decision making in the face of uncertainty is less conservative, but it is again able to guarantee the voltage compliance, operational compliance. Now the work that I just shared with you was done by Dr. Firdaus. I don't have the research activity only in that area. I have also many other research interests, particularly I started with power transmission control. That's how we wrote a couple of books about a decade ago, and then their second version appeared, and then been translated into Chinese and so on. And now recently also have worked on the simulations, the power systems renewables, and dynamic state estimations. So this is control, modeling, monitoring, and estimates. These are all my people. There are about 3 Marie Curie fellows, Dr. Campitsis, Dr. Wu, and we got 2 postdoc, and then these are all the PhD student right now I have in the group. I've been extremely privileged to receive research funding from EPSRC and distribution network operator, transmission network owner as well as operator, like this FinGrid, StatNet, National Grid in Finland, Norway, and England, UK. We also have the vendors like ABB, GE, and Alstom helped us. I was also involved with a couple of a little bit of work for United Nations for clean technology development. The methodological report, etc., etc. So that's the work that I'm very happy to present to you, and I'm now finished with the presentation, so you could go back for the questions, right?
Okay. All right. Thank you, Prof, for very informative and interesting presentations. I would like to open any question from the participants. Any question, Dr. Kanendra, from the participants?
I cannot see your participant. I mean, who are the people? I don't see even who have.
They are looking through the YouTube and the Facebook, Prof. They are
But in this
follow
case,
through the Facebook and YouTube.
yeah, but I don't see the name of the people. So, what kind of platform is this? I don't know who you are talking to. I mean, if you're talking in Zoom or if you're talking in, say, WebEx or Microsoft Teams, at least you know the people who have joined and their name. And here we are talking to someone whom I cannot see, their name. You think this is
Yeah,
the,
yeah, yeah.
the best?
Because they are follow us through the YouTube and the Facebook. So most of the participants they are follow through that platform, Prof.
Yeah, how many
So
people
we
are
cannot
following?
see how many. Okay, any question from the
Haven't
Kanendra?
haven't yet.
So there is no question. I cannot see the people and all, but this is not the right platform. Then for it, we should go with a proper WebEx. Yeah, I mean, for DLP, IEEE gives you WebEx anyway, right? For DLP
Uh,
organization, yeah, IEEE gives you
mm-hmm.
free WebEx for people to register and do it.
Okay. All right. So we never notice on that. So basically, we are using this kind of platform, Prof, for any event that we have conducted previously.
Okay, so then you need to do fill the form and send back to the DLP coordinator. How many
Uh-huh.
people attended and whether they are PS member or not or IEEE member or not. Those
Okay, okay.
report has to be those report has to go to the DLP coordinator. Then it will go to
Yeah,
the
yeah, exactly.
chapter VP. So
Uh,
how many people have registered for this?
is it about 30, if I'm
Yeah, we
mistaken?
had like 30 participants who registered.
Yeah. So that name, that list of registrants has to go to the DLP coordinator Nirmal Nair in New Zealand, and
Yeah,
then
yeah.
also this will also come in PS News as chapter event. So that you have
Okay,
done this in
I,
Malaysia
I,
chapter. Yeah. Yeah.
Okay.
okay, there's one question posted by the Abdul Malik, Mr. Abdul Malik. How can machine learning technique be integrated to enhance the Volt-Var coordination efficiency?
Well, I don't work on machine learning. Definitely, uh, after you generate lots of scenarios, then you could utilize some of the scenarios to train your um, the machine learning algorithms. It can be like say deep learning method or whatever, and then the
Mhm.
other one you could utilize to validate. But in this case, we have a nice set of mathematical equations and model. So if I have model of the uncertainty as well as the model of the system reasonably good, I think it would be difficult to for the machine learning to beat that. So we are already talking about epsilon and gamma, which are say 10 to the power of -6, and that. So the robustness as well as the confidence are quite good, isn't it, in this? Okay.
Okay, all right. Thank you. Any more questions? Prof, I have one question, Prof.
Yeah.
At the important remark you mentioned about the nodal uncertainties need to be corrected. Can you elaborate a little bit more on the nodal uncertainties?
Oh, the nodal uncertainties is when the in the nodal uncertainty, what happens for every in node you have the PV. So you write the P
Okay.
injection equations. Now you do not know that value of the P because you can only forecast how much it is going to be. You can measure, but the measurement will have again noise. So because you do not know for sure how much P is coming, so that injection equation, the P and sum of all these things, so that equation has got some randomness. So that is the uncertainties. So you need to handle that uncertainties by generating many scenarios around that, and then pass that to test whether this voltage magnitude violation probability is met or not met. So if you have P and Q, like
Okay.
P is coming from a fixed generation source, so you know PQ. So that equation is deterministic for you. But when the P is also including the PV generation at a node, so then that generation is not certain value to you. So you cannot have a deterministic thing. So then this nodal P injection becomes uncertain.
Okay, this question posed by the Dr. Muhammad Fuad Faisal. Okay, based on your studies on the impact of VVO, what is the estimated figure on each percent of voltage reduction on reduction of energy consumption?
We don't actually, we don't reduce the voltage. We are not working on that conservative voltage reduction to reduce the energy consumptions. We are optimizing the loss in the network. So we don't touch the demand. Whatever demand is there, that is there. We are meeting the demand.
Okay, any more questions? Okay, at night, the PV system fits the kW but not kilowatts. How this affects the VVC algorithm?
Yeah, that at night, then what happens is this: it was like the full capacity of the PV inverter is available to you as a reactive power source. Like A PG square plus B PG plus C. So at night PG is 0. So whatever is your A and B, that is not effective. And whatever C is there, that becomes your Q. Okay. So Q, what was Q? Q was A PG square plus B PG plus C. And PG square plus QG square always has to be equal to the capacity of the converters. So now at night PG disappears, so whole of QG becomes the S MVA, the total MVA, the total kilovar that you said. So that means this will affect the VVC algorithm in a sense. It will do that means it will take the responsibility of the Volt-Var control now more at night, and then it will relieve the tap operation, etc., to every hour you see that we have to have this optimization of the tap positions. But then you will see that at night your tap would not move as much as it will move during the day every hour when you do these computations.
Okay. Again, question from Mr. Romali. Does the transformer life cycle play any role during Volt-Var coordinations?
Yes, it does. That's why we are optimizing that. The life cycle of a transformer is not a transformer life cycle, a transformer tap changer life cycles. I thought you wanted to mean, right? So, yeah, the transformer tap changer life cycle is what? 30 years. You have 3,000 operations a year, say, or 1,000 operation a year, about 3 to 4 operation every day. But because of the PV, if you don't optimize, it can be 30 to 40 operations every day. And if 30 to 40 operations, then the tap changer life will be reduced and reduced. So does the transformer life cycle play a role during Volt-Var coordination? Yes, it does, because your Volt-Var coordination has to be done in a way that you don't actually reduce the life cycle of the transformer tap changer.
Okay, again, the second question from Dr. Muhammad Fuad. The operation of OLTC is based on the setting of AVR. For the VVR project, will you bypass this function? Utilities set the VR to ensure AVR to ensure compliance to the voltage regulation requirement set by the energy regulator.
Yeah, this that the voltage regulator set point and OLTC set point, whatever reference we set there, that will come from the output of this optimization now. So the optimization output will take over what would be the setting for the AVR and all. So AVR will not be able to operate on the basis of the local measurement of the voltage, etc., etc. It will not be. It has to be all instructed every hour what should be the position. And once you get that position, the automatic voltage regulation actions in that local loop will be disabled. It will be disallowed.
Okay, any more question?
That's all.
Okay, bro. I ask very basic question. In your study, you choose a PV. We know that at UK, we have they have installed with the wind turbine. What that makes you interest to choose PV rather than wind turbine
No,
in these
PV,
studies?
P is, P is normally in the UK, you got loads of PV in the distribution level.
Uh,
Yeah, we have altogether 13 gigawatt of PV in UK.
okay.
Big
All right.
farms, medium farms, small farm, rooftop, and all. So,
Mm-hmm.
at distribution voltage level. So PV is mainly on the distribution voltage level, 11 kV, 33 kV, with a big wind farm. Whereas big solar farm. Whereas the wind farms, they are on the offshore, they are like 1000 megawatt, 2000 megawatt. They come through
Oh,
400 kV network. They are in the transmission system. This one we are talking about
okay, okay.
distribution system Volt-Var control. So PV is more relevant.
Okay, you mean that's the wind turbine mostly focus on the generations? Am I
Wind
right?
turbine mostly, PV also focus on generation, but wind turbine generation is at high voltage level. So that goes to the
Okay, okay. All right. I see, I see.
the transmission system. So then that
Mm-hmm.
becomes the Volt-Var control of the transmission system. This one we are talking about a distribution network. So PV is most important.
Okay, all right. Any more question, Dr. Kran? Maybe we can
I
accept one more
think
question.
that's all. No, that's all.
Okay, I think that's all the question from the participant, Prof. So thank you again for your very interesting sharing under the LP programs. So over to you, Dr. Canada.
Oh, sorry, Prof. There's one more question that just came in.
Okay, sorry. There's one more question. Okay. The size of the capacitor bank connected can influence the extent of parallel resonance in the power system. Okay, what is the comment on the VVO studies and potential parallel resonance? Okay, Mr. Fuad mentioned about the effect on the parallel resonance.
Yeah, that's a very, very good point. So parallel resonance, you have capacitor, and then the network. The capacitor banks, they come from the set, whatever set you have there. So that means they are already there. So when they have been planned, probably they have done some studies to see that there is no parallel resonance. And if it is not done, and then if you bring these, so necessarily that has to be done. The parallel resonance study is uh, the parallel resonance possibility cannot be checked in this process, because you always have you are always maintaining this voltage in this. But one thing you could indirectly address is, because you are calculating your voltage range 0.95 to 1.05, if there if there is parallel resonance, naturally the voltage will be out of bound. So one process, because you always have I think some reflection is coming. So
sorry.
yeah,
Okay, this reflect. All right. Okay,
yeah.
carry on, Prof.
Yeah, we don't need to. We cannot guarantee that it will not happen, but we have to check that, given all your setting that you have got, and then what is that frequency that you have. Resonance only happens when you excite actually that resonance frequency with a signal of that frequency, right? So we are now all talking about P, Q, V, etc., all power frequency. So naturally, we do not know whether it will have any issues. So, but that is a study, separate study that has to be done on time domain, or the model has to be different for this.
Okay. All right. Any more question, Dr. Kanandra, from the
No, I
floor,
think
from the
that's
participants? Oh,
no.
okay. That's okay. Over to you, Dr. Kanandra. Okay. Again, I would like to give a big thank to you, Prof, for your kind participant and we call it the LP program under IEEE PES Malaysia. So again, big thank for you, Prof.
Okay, it's my
Okay.
All right.
pleasure. I really enjoy the
Okay.
All right.
questions. I really like the questions.
Thank you to Professor Bikesh Pa for his distinguished lecture series on his lecture topic. And also thank you to Associate Professor IR Dr. Ahmad Farid Abidin for moderating this event. And we'll also like to thank all the participants who have joined this event via our Facebook page and also our YouTube page, and asking the questions to our distinguished lecturer today. And with that being said, thank you to all, and please do join us for future events from IEEE Power and Energy Society. Thank you.
Okay,
Okay. Thank
so
you
if
very
I
much.